application of differentiation to understand behavior of the function, the intervals in which a function increases or decreases according to the derivative being positive or negative. And then we had also discussed about domain range of a function, okay, the difference between natural domain and some kind of specified domain or constrained domain. And according to the domain, the range of the function and therefore the global maxima and minima. And we had also seen that when the behavior of a function is such that it alternately increases and decreases within the domain, then apart from the global maxima and minima, which is basically to do with the range of the function, there are also individual peaks and dips through which the function goes. So the peak points, they are called the local maximas, and the dip points are called the local minimas. So today's lecture will be concentrating more on the application of differentiation to do with the local maximas and minimas. Anyhow, so let's begin. So mostly we will concentrate on the concept of local maxima and minima today first. And then we'll also see some examples where we are investigating not only local, but global maxima and minima along with local maxima and minima. So let's start with, once again, understanding what is local maxima and minima first, and then how we use the derivative of a function to calculate the local maxima and minima. So if a function alternately rises, then decreases, then again rises, and this process might repeat more number of times also. So if this happens within some specified domain of the function, so if this is, let's say, the function fx, now we can see that at a point like this, where the function is switching its behavior from increasing before a to decreasing after a, and again at a point like this, where the function is switching its behavior from decreasing before b and increasing after b. So at two such points, if we draw the tangent to the graph, we can see that the tangent will be perfectly horizontal. So the slope of the tangent will be 0. So these are our significant points, okay, where the function's rate of change becomes 0. Okay. So basically what we are going to understand that if fx is increasing at x less than a and fx is decreasing at x greater than a, then it will imply that at x equal to a, the function has reached a peak sort of point. Okay. So that peak sort of point is called local maxima. And also we can see that f prime x is negative for x equal to a minus delta x, that is x less than a, and f prime x is positive for x equal to a plus delta x, which also means that f prime x is equal to 0 at x equal to a. So that also means that at position of local maxima, which is basically x equal to a, the slope of the tangent is equal to 0. Okay. So as you can see that overall the behavior of this function here is such that at x equal to a minus delta x, the slope is positive.
So, but
At
they
x,
have written f prime x is less than 0.
oh sorry, yeah, it should be greater than 0 and should be, yeah, thanks for pointing out, it's just reverse. So here it is positive, okay, because the function is increasing before a, and after a it is becoming negative because the function is decreasing. Okay. Yeah. So at this point you can see the slope is positive at x plus delta x, and similarly if I draw a point after, then the slope is negative. Okay. But at x equal to 0 you can see the slope is 0. So that becomes the property of the local maximum. Whereas now if you similarly investigate what is happening at the point B, okay, so you can see that at the point x equal to B, for x less than B, the function was decreasing. For x greater than B, the function is again increasing. So at x equal to B, the function has a dip point. So that is what we call the local minima point. The function reaches a local minima at the point x equal to B. And again, from this, you can also understand that the derivative of the function is going to be this time negative for x equal to B minus delta x. It's going to be positive for x equal to B plus delta x. Okay. And the derivative is going to be 0 at x equal to B, which is the point where the function has reached the local minimum. So once again, you can see that in the graph over here, that if I draw a point before B, the slope is negative. If I draw a point after B, the slope is positive. But precisely at the point B, the slope is 0. Okay. So this kind of behavior, that the slope is changing from positive to 0 to negative, is the point where the function has a peak or local maxima. And that kind of behavior where we have the function's derivative changing from negative to 0 to positive, which is happening at the point B, the function reaches a dip kind of point. So we have the local minima. Okay, now all this analysis can be very lengthy for, especially a complicated type of function. So what we will see today is how we can use some further analysis of differentiation to develop a very quick sort of shortcut method that, given the formula of a function, given the expression of a function, very quickly we can analyze which are the points where the function has local maxima and which are the points where the function has local minima. So anyhow, so this is a basic recap of what we discussed last time about local maxima and minima. Just go through this once. You need not write down this again in detail because it's there in your notes. Okay. And let me know if there's any doubt about this part. The analysis of the point x equal to B, which I've written here, and the analysis at the point x equal to A. They've written here. So basically the analysis of local maxima and minima. And as you can imagine, the graph of the function can be such that it has any number of peaks and dips, including 0. A function may be such that it does not have any peak and dip, so it does not have any local maxima or minima, or it has only local maxima, or it has only local minima, or it might have any number of local maximas or minimas. If you just visualize a sine wave, going from minus infinity to plus infinity, you'll see that it has infinite number of peaks at all the points like pi by 2, 5 pi by 2, and so on and so forth. Whereas it has a dip at all sorts of points like 3 pi by 2, 7 pi by 2, 11 pi by 2, etc. So it has alternate peaks and dips. So any number of local maximas and minimas are possible for that matter. And for the moment, just now, we won't worry too much about domain range and global maxima and minima. We'll bring that back into the analysis later. Let's right now concentrate on the analysis on local maxima and minima. Okay, so I'm hoping that this part is all clear to all of you, right? Now we will see another application of differentiation. And that is something called, you might have heard about this, something called second derivative of a function. And we'll see how this analysis of second derivative helps us in analyzing about maxima and minima. So what is second derivative of a function? It is literally rate of change of rate of change. Okay. So for a function y is equal to fx, what we mean by the second derivative, literally in terms of definition, is that it is rate of change of the derivative. And since the derivative itself is the rate of change, so basically it means rate of change of rate of change. So this is given a special symbol. This symbol, we read it as d2y by dx square. Okay. And it is basically second derivative of y with respect to x. So that is nothing but rate of change of the rate of change. So in other words, for y is equal to fx, we write the derivative as f prime x. So now d2y by dx square, which is rate of change of rate of change, becomes nothing but differentiation operated on this, on f prime x. So in short, we write this as second derivative. Sometimes we write it as f double prime x to show that we have differentiated twice. Okay, so this might be a little confusing initially. So let's just understand it with a quick example, then it will become clear. So
So
for
how would
example,
we apply chain rule in this?
chain rule is not necessary, beta. Okay, chain rule is a method of differentiation. Okay, so if, for example, the function is composite, then to find the derivative f prime x, we'll use chain rule. And then the derivative will also be a composite function or something like that. So again, to differentiate it once more, we'll have to use chain rule. Understanding the point?
Yes, sir.
So we'll come to composite functions and all, but let's first understand with a simple sort of function. Suppose my function is x cube. Okay, so then we will say that fx is equal to x cube. So derivative of the function, what we in short form write as f prime x, will be differentiation of x cube. So that will be 3x square, as we all know. Now what about the second derivative of this function? It will be differentiation of differentiation. Okay. So therefore second derivative, which is now called what? It is called d2y by dx square, or in short form we write as f double prime x. So that is going to be derivative of f prime x. So that is 3x square's derivative. So this will become 6x. So we will say that 6x, this is the second derivative for the function y is equal to x cube. So it is the rate of change of rate of change. Now, practically, you can think of one very nice example of this, which we are all familiar with, that velocity is the rate of change of displacement with respect to time, and acceleration is the rate of change of velocity. So acceleration becomes the second derivative of displacement with respect to time. We'll come back to that example also. First, make a quick note of the definition and make sure you understand the steps for this example. Now we'll see what is the importance of second derivative apart from acceleration, which I told you, which will come in kinematics when we come to that chapter. But here it has a significance for us for our calculation of local maxima and minima also. Okay. So just make a note of this and just be back in a minute.
Done, sir.
So when you study advanced calculus in mathematics, you learn that there is not only second derivative, but there's third derivative, fourth derivative. We can go on differentiating a function. So there is some such thing as nth derivative. But here in physics, we will not really require nth derivative so much. So right now we'll just get familiar with derivative and second derivative.
So, but in this example, after third derivative, we would get a constant, right?
Sorry, in this example?
Y equals to x cube. After third
Uh,
derivative, we cannot differentiate it more.
yeah, if we differentiate the second derivative, we'll get a constant. And then if we differentiate that one, we'll get 0. So a function may have only certain number of derivatives as far as nth derivative is concerned. But then there are certain functions which have infinite number of derivatives. Like if you think of sine x,
Yes, sir.
So e raised to x.
yeah, e raised by x is also a very good example. For that matter, even ln x, you can go on differentiating it, you'll keep getting some derivative. Okay, so as I was telling you, in kinematics, if you're talking about one-dimensional motion or straight line motion, so you have a direct application of that for a particle or a body moving along a straight line, let's say x-axis. Okay. If its position x at any instant of time t equal to t is given by some kind of a function like this, that x is some function of time. Okay, so for example, we might have x is equal to, let's say, 5t plus 2t square. So you can see obviously this is an example of a uniformly accelerated body, because the displacement, you can say, from x equal to 0 at t equal to 0 to x equal to x at time t is that kind of ut plus half at square kind of function. So it's uniformly accelerated. Okay. So suppose we have something like this, then we know that the instantaneous velocity, the definition of instantaneous velocity as per the proper calculus definition is dx by dt. Okay. Earlier we had seen it is delta x by delta t for a very small interval, but now we give the perfect calculus difference, the calculus definition that instantaneous velocity is instantaneous rate of change. So by definition, it is delta x by delta t, not for delta t being very small, but for delta t tending to 0. So that becomes dx by dt. Okay. And so in this particular example, the instantaneous velocity will become differentiation of 5t plus 2t square, let's say. So that becomes 5 plus 4t. Okay. So you can see this is becoming v plus at, sorry, u plus at, where this was ut plus half at square. Okay. Now further, instantaneous acceleration, the definition of this becomes what? That it becomes rate of change of velocity with respect to time. Instantaneous acceleration is instantaneous rate of change of velocity with respect to time. Of v with respect to t. So that becomes this. Okay. Now you can see that since v is equal to dx by dt, so we can also say that a is equal to rate of change of position with respect to time, or acceleration has a relationship with position that it is second derivative of position with respect to time. So that is like one example where you can directly see there's a physical significance of this operation of second derivative. Just as we say that velocity is derivative of position with respect to time. V is derivative of x with respect to t. So here acceleration is becoming second derivative of position with respect to time. This is the same thing as derivative of v with respect to t. So now you can see in this particular example, acceleration will become dv by dt, which is differentiation of what was dx by dt. So you can see that in this particular example, aside from the general definition, so this particular example, our acceleration will become 4. and depends on what units we have used. Suppose x was in meters and t was in seconds, then here v is in meter per second, and here acceleration will be in meters per second square. So immediately when we complete calculus, for example, when we come to kinematics, we will see that so many of the definitions itself are directly related to the operations of calculus. Okay. Not just differentiation, which we have seen in this example, but also integration, which we will see in future. So one of the areas in which of physics in which calculus's application falls most naturally is kinematics. And in fact, indeed, if you study historically how calculus was developed by Newton in particular, I told you earlier that Newton and Frank Leibniz were the two chief contributors to the invention and development of calculus. So particularly Newton was doing a lot of work related to Newton's laws of motion and the motion of bodies and kinematical equations. So during that process of working on those physical principles, he developed most of this part of calculus. So now a lot of things we take for granted once we study the basic principles of calculus. But at that point of time, like, it was major breakthrough in physics and mathematics. So this is an example of a physical application, okay, of concept of second derivative. Now let's do a bit of practice before we come to our applications. So I have a function, let's say sin x plus 2 cos x. Okay, find dy by dx and d2y by dx square first. Okay. And secondly, find the values of the derivative and the second derivative at the point, both of these at the point, let's say x equal to pi by 6. So let's see how we deal with this type of question. So it is just about systematically applying differentiation and the principles of differentiation. Okay. But now adding to that the concept of second derivative, that it is just applying differentiation once again, but on which function? Not the original function y, but on its derivative, which is dy by dx. Or applying differentiation not on fx, but on f prime x. Yeah, people, I'm waiting for your answers. Oh, very good. I've got them. Yes, Vineet, correct. Om, correct. Shambhavi, correct. Very good. The value is correct that you have sent. Perf correct. Very good. Tanay correct. That is for second derivative, Tanay, what you sent.
Sir, I've sent for first derivative also.
So you sent earlier for first derivative. Yeah, correct. That was correct. Yes, Sai, correct. Good. Okay, Shreyas, correct. Very good. So as you can see that if you're familiar with differentiation, you have no problem with anything like this. Okay. Of course, if it is a composite function, the process might be a little more complicated. Here, luckily for us, it is not a composite function. So the first derivative was just differentiation of sin x plus 2 cos x, okay, which you can see will become cos x minus 2 sin x, because you know derivative of cos is minus sin and derivative of sin is plus cos. So our derivative is this now, cos x minus 2 sin x. Okay. So our second derivative, d2y by dx square, we'll just have to repeat this differentiation, but on what now? On dy by dx. So I will substitute dy by dx from here, what we got earlier, as cos x minus 2 sin x. So now I'll see that differentiation of cos x is minus sin x. Differentiation of sin x is cos x only. So I get this. Some of you might have got the algebraic signs little bit mixed up. That is, just make sure that you're clear with this. Okay. If I take the minus sign common, you can see I get this. So this is the answer to the first part, derivative and second derivative. Now the second part, I have to just find the value. So I want to find dy by dx firstly at x equal to pi by 6. So that will be cos pi by 6 minus 2 sin pi by 6. Okay. So cos pi by 6 is root 3 by 2, as you all know, and sin pi by 6 is half. So it will become root 3 by 2 minus 1, approximately 1.73 by 2 minus 1, whatever. Okay. And similarly, b part, d2y by dx square at the point x equal to pi by 6 will just become, now this is the second derivative, so it is minus of sin pi by 6, okay, plus 2 cos pi by 6. So it is minus of 1 by 2 plus 2 root 3 by 2. So it is minus of half plus root 3. Okay. So this is the value of the second derivative. This is the value of the first derivative at the point x equal to pi by 6. I'm not solving it numerically further. You can always reduce it if required. Yes, I'm just going through all of your answers again. Okay, now let's look at something a little bit more challenging. So remember, one of you were mentioning what happens if you have to use chain rule to get second derivative also. So let's look at an example. So we have the function fx, or let's say the question just directly gives us the function. So that is e raised power x square. So as you can see, this is a composite function. Now I want to find f double prime x and f double prime of, let's say, 0. That is this. What this means is, this means the value of the second derivative of fx at the point x equal to 0. This is the meaning of saying that I want to calculate f double prime of 0. Okay, so this time you'll see that the differentiation and the concept is still the same. It's very simple, but you will have to put in little more effort, more number of steps, because each time you differentiate, you'll have to make use of chain rule and probably a little bit more also after that. So just try and identify what all principles you'll have to use, or what all properties of differentiation.
Sir, I have sent the answer. Will you please cross check?
Yeah, got the answers, people? Very good. So you should be getting 2. Yes, most of you got that. Very nice. Okay. So let's see. So let's start with the first thing, how to get the second derivative. So given the function, we can't directly find second derivative, of course. The first step is to find derivative. So f prime x, we have to differentiate e raised power x square. Okay. Now I'm going to do this in 2 ways. One is the direct method, which I expect most of you should be able to do by now, as well as the the step-by-step method. So for composite function, One is the direct formula, you can say, for differentiation. So if y is equal to f of gx, then the direct formula method is that dy by dx is derivative of f operated on g multiplied with derivative of g. Okay. And of course, you should not think of this dot like a dot product. Okay. According to vector algebra, this dot would be wrong here because you can't take dot product of two scalars, but you might understand that it's a multiplication of these two. So I can apply this directly over here. So when I look at this, I can understand that this is f of gx, where what is g? It is x square. And what is f of gx? It is e raised power gx. Right. So directly now, f prime x will become what? Derivative of this. So e raised power gx into derivative of this, which is 2x. So it is e raised power x square into 2x. Or we can say 2x e raised power x square. So this should be the derivative. Okay. So if you practiced enough by now, especially exponential based or logarithmic based or sine cos kind of based, composite functions, you should be able to get the answer directly like this, literally in one step. Like even all this I've just given for explanation. You should be able to come from the formula of the function directly to this. Okay. However, if you are still a little bit, you need to practice more, then you can always look at the chain rule and substitution method. So in that step 1, we substitute gx as z. So y becomes f of z. Step 2, we apply chain rule. Dy by dx is equal to dy by dz into dz by dx. And step 3, we resubstitute. So on resubstitution, this becomes this. Same formula. It's f prime of gx into g prime x. So basically what we get from application of chain rule, this formula directly I'm applying over here. Okay. So if you're still finding it difficult to directly come to the answer, don't worry. You just need to practice a little more. But if with enough practice, there will come a stage where you'll be able to do this correctly. Okay. So the alternate method is the chain rule method. So in that, for the function, I would substitute x square as z. So y will become e raised power z. So this is my first step. My second step this. So that would become e raised power z into 2x. And my third step, resubstitution. So this z here would be resubstituted. That will give me. So it's not really that the stepwise method also takes that long. So this is now just the derivative. Remember, we have to find the second derivative. So we have to differentiate this once more. Now you notice that when we are going to differentiate this once more, it's a product of two functions. One is the linear function 2x, and the other is again the same function e raised power x square. So now second derivative. This is going to be derivative of the first derivative. So this is going to be differentiation of 2x e raised power x square. So this we will now use the product rule, that differentiation of, let's say, u into v becomes uv prime plus u prime v, like this. Okay. So basically it is, you can take the 2 outside, differentiation of x into e raised power x square plus x into differentiation of e raised power x square. So, okay. So as you can see, this will become 2 e raised power x square, okay, plus 2x into this differentiation. Now this differentiation we already seen above. E raised power x square's differentiation is 2x e raised power x square. So what we should be getting now is 2 plus 4x into e raised power square. So this should become our second derivative. So just check all of you that your steps are correct. So I can even take this 2 common. So this differentiation that we have done, this one here to this step, this is again the composite function chain rule. Okay, that we got from here. Okay, so now that I have got the second derivative, now second part I'll find its value. Is nothing but is the value of the second derivative at the point x equal to 0. So I'll substitute x as 0 in this. Okay. So that will be just 2. So most of you sent me the answer. You got this correct. Very good. Okay. Okay. So now having learned about second derivative, okay, let's come back to our analysis of local maxima and minima, and let's see how second derivative is something that we can use in the analysis of a function for this purpose. Okay, so let's understand the application of so we'll use something called second derivative test. So I'll explain what that means. Okay, so again, seeing that sort of general perspective of a peak point and a dip point. Now, if we talk about not only the function and its rate of change, but we also talk about the second derivative, we will see an interesting aspect of the nature of a peak point and a dip point. So if you see, as we had discussed at the point E, let's say over here, okay, this is the case, but at a point before A, the slope is positive, and at a point after A, the slope is negative. So we'll come back to the minima point. Let's first concentrate on the maxima point. So for this given function, what you can see here is that at x equal to A, the function has a peak, or what we call local maxima. Now you can see that f prime of A is equal to 0, but f prime x is changing from positive value to negative value as x goes from x less than A to x greater than A. So if I think of separately now, if I think of what is happening to the f prime, what is happening to the derivative of the function, that has a very interesting behavior at the point E. So side by side, let's say I'm analyzing the derivative of this function now. So instead of analyzing fx, I'm analyzing the derivative. So what I'll see is that at the point A, the derivative of the function now has this kind of behavior, that it is going from positive value to 0 to negative value. So it must be like this, it must be having this kind of a behavior. Okay. So we can say that at x equal to A, f prime x has a behavior that it is decreasing with respect to x. So as x is increasing across A, the f prime x, if this is the function f prime x, that has this kind of behavior, that before A, it has a positive value, after A, it has a negative value. Okay. So it is changing from positive to negative. That means it is decreasing. Okay. So f prime x is decreasing at x equal to A. So what that means, that rate of change of f prime x should be what kind of thing? It should be negative at x equal to A. Okay. So that means what should happen? Second derivative at A should be what kind of value? It should be negative. Okay. So please correlate these two graphs. Okay. Understand this point very carefully and let me know if you're having any doubt understanding why this is happening. That at the peak point, the derivative of the function is going from positive to 0 to negative. So second derivative of the function should be negative because the derivative itself is decreasing. So its rate of change should be negative.
So if it was going from negative to positive,
then it would be positive, and that you can see is happening at the dip point.
okay.
So now you understand that second derivative gives us some useful information at a point where the function is having 0 derivative. A and later we'll see this point B are both points where the function's derivative is 0. But if you look at the second derivative of the function, it has a different nature in A and B. At A, because there's a peak, so the second derivative is going to be negative, whereas at B there's a dip, so the second derivative is going to be positive.
Sir,
Yes.
sir, but at A derivative is 0. So second derivative would also be 0 only, no?
No, beta. Like, see, second derivative is the value of another function. No? Like, suppose we have the function y is equal to, let's say, sine x. Okay. So what is the derivative? It is cos x. And what is the second derivative? It is minus sine x. So now see, at a point where cos x is 0, is minus sine x 0? No, no.
Okay, sir.
No. So yeah. So when we look at the examples, this will become even clearer. But see, even without the example, you can understand this from the graph. See, second derivative अगर 0 होता उस point पे, then f prime कैसा होना चाहिए था? It should have been flat at that point, ना? But you can see f prime is not flat because just before a, f prime has a positive value, and just after a, f prime has a negative value. So f prime itself must have a negative slope, na, at that point a.
Yes,
Now you
sir.
understood my point, na?
Yes, sir.
So at the point a, f prime cannot be having a 0 slope. F prime must be having a negative slope. So that means f double prime is negative. Arya, you were asking about the previous question. No?
Yes.
Hope that point is clear now. Sorry, I missed your message. That 2x into 2x thing you were asking. Yeah, Jitesh, I'll answer your question.
Yes, sir.
Yeah. Yeah, Jitesh, you have asked that we have to find the values of first derivative and then relate it to the second derivative, or finding only the values of the first derivative will work. No, so that's what I'm explaining, that when we want to find uh, the local maxima and minima for a given function whose graph we don't know, but directly the function's formula is given to us or expression is given to us. So we will have to find both the derivative and second derivative of the function, and we'll have to use this method we are developing now called the second derivative test. So far what we have learned about this, that at a point of local maxima, what happens, that derivative is 0 and second derivative is negative. So what this is showing us in conclusion is that
Second derivative is decreasing.
so this is showing us that therefore for y equal to fx, if at the point x equal to a, the derivative is 0 and the second derivative is negative, okay, that means that the function has a local maxima at x equal to a. So if this function is showing this kind of behavior, that at a particular point the derivative is 0 and the second derivative is negative, that means it's having a local maxima. Now
So
before
if the derivative is negative, if the derivative is negative, it will mean that it has a local maximum.
second derivative is negative beta.
Yeah,
Derivative
second
has to be
derivative.
zero.
Yeah, second one.
Okay, understood now. So we'll just take a quick example of this before we proceed. Acha, you can write down this point. Now, similarly, we'll see that we'll get a condition for minima also. Now you can say that this thing that we have written, this has become the condition. This and this, it's an and condition. It's not an or condition. Both this statement and this statement have to be satisfied. That is, derivative is zero and second derivative is negative for that point to have a local maxima. So this is the condition for this statement, that we are having a local maxima at x equal to a. So for example, suppose we have the function y is equal to, let's say, 4x minus x square. Okay. Now we say that find a point or points at which dy by dx is equal to 0 and analyze from second derivative if such a point has local maxima. So I'm not talking about local minima yet. I'll come to that, but let's just understand from this. Okay. So we have to just apply this condition for local maxima now. That derivative should be 0 and second derivative should be negative. Okay. So let's apply this concept to this function now. So the function is 4x minus x square. That means the derivative of the function is what? It is 4 minus 2x. Okay. And the second derivative of the function is the differentiation of this. So it is minus 2. So it's constant. Now, the value of second derivative is same everywhere. So this is the first step, that we find the derivative. Okay. Find dy by dx and d2y by dx square. First derivative and second derivative. Now the second step is we want to find where dy by dx is 0. Okay. So therefore, dy by dx is 0 implies that f prime x, which is basically 4 minus 2x, should be 0. So that gives us only one single point here. It gives us 2. There's only a single unique point where this is happening. Okay. So that means the slope of the function is 0 at which point? At x equal to 2. So from our previous knowledge, we understand that x equal to 2 is either a peak point or it's a dip kind of point, because these kind of points have 0 slope. Okay. But to understand that whether it is a peak point or whether it is a dip point, we will use this thing, that if it's a peak point, then second derivative should be what? Negative. Okay. So, and f double prime x is equal to how much? F double prime x is minus 2. Okay. So this is at all points, irrespective of, okay. So this includes the point x equal to 2. So now from this, what we can say, that we can say that the derivative of the function at 2 is 0 and the second derivative of the function at 2 is negative. So that means this satisfies the condition for what? It satisfies the condition for local maxima at x equal to, so the function must be having a peak point at this. Okay. And I will show you again the proof of this by another method also, which was the interval method that we had discussed last time, that we can analyze the function for the intervals in the domain where the function is rising and dropping, and from that we can understand where the function should have a peak. But you can see now that this is so much easier. For analysis of local maxima, I had to basically just do 2 steps. Step 1 was find dy by dx and the second derivative by differentiating and redifferentiating. And then step 2 is just look at the values of second derivative at the point where the derivative is 0.
Yes, sir, but if derivative becomes very complicated, then this step will become like very difficult if second derivative was to be found, right?
Yeah, it will become complicated. But see, the thing is, if derivative is complicated, then even your method of analysis of increasing, decreasing will also be complicated. No?
No, so but if we find factors and if there's a denominator, so if we go to find derivative, So it will become complicated. But if we do
नहीं
it
नहीं देख,
normal basis,
अगर factors निकालना आसान है ना, तो even second derivative will be easy because it's a polynomial only, ना.
yeah.
You understanding my point? The
Yes.
difficulty comes when it's a very complicated composite function and all that, na. So then both the things are complicated.
Okay, sir.
You understanding the point, na?
So it will depend ki which method will be
It actually
easier.
depends. Like, see, there are infinite types of functions possible, na, in the world. So like, depending on the complexity of the formula of the function, analysis might be simple or it might be complex. But the thing is, we have both the methods. And typically speaking, this method is easier if we just want to find local maxima and minima. Whereas if we want to do the full analysis of the graph of the function and all that, then what we've learned earlier, that increasing, decreasing intervals and all that, that is also very useful, right?
Yes, sir.
But अगर मुझे precise एक ही चीज चाहिए, that what is the local maxima, what is the local minima, then this precise method is much easier, that we do what is called the second derivative test. So I'll elaborate on all the steps when we discuss about minima also, but you'll see that it's reasonably easier.
Yes,
So
sir.
before this, we used to do the wavy curve method. So
So
can that be easier in some cases?
sorry, come again, beta, a little bit louder, please.
Before we learned the second derivative, we used the wavy curve method to do
Yes,
this.
yes.
So
है ना? Where
can that
we
be
were
easy?
able to factorize the derivative, we can use the wavy curve method, है ना?
Okay, sir.
But even that is little bit lengthy, na? To factorize, then use the wavy curve method, then analyze. It's a little bit lengthy compared to this, no?
Yeah.
Okay. Okay, so this step that we have written over here, this is called the second derivative step. That we are investigating the second derivative. Okay. So in this, what we do is we first we solve f prime x equal to 0. Okay. And then we investigate, we test the value of f double prime x at these points. So in this case, there was only one point, which was x equal to 2, and we investigated second derivative, that is uniformly minus 2. So then we came to this conclusion. Okay, we came to the conclusion that derivative is 0 and second derivative is negative. So that means it's satisfying the condition for local maximum. So now what that tells us, that therefore the function, what was our function? It was 4x minus x square, no? Yeah, has a local maxima at the point x equal to 2. So now we can also see that at the point x equal to 2, the value of y is how much? It is 4 into 2 minus 2 square. So it's equal to 4. So the local maxima its value is 4, but it occurs at which point? It occurs at the point 2. So what we expect is that the graph of the function should reach a sort of temporary peak at the point x equal to 2. And the value of the function at that peak should be equal to y is equal to 4. So it has the local maxima at this point. Okay, now if I went by the wavy curve kind of method, in this case, I won't even need the wavy curve because it's a simple function. Okay, so alternately, what we could do is we could have analyzed the behavior of the function. Okay, so the function was 4x minus x square. So derivative of the function was 4 minus 2x. So we can see that it's this. Okay, so we can see that the function's derivative is negative for 2 minus x being negative. So that means x being greater than 2. And the function's derivative was positive for 2 minus x being greater than 0. That means x is less than 2. So this analysis was telling us that therefore this function is increasing for x belonging to minus infinity to 2, and then decreasing for x belonging to 2 to infinity. So x belonging to minus infinity to 2 and x belonging to 2 to infinity. So on the number line, we could have thought that, okay, we have only one critical point, which is 2, and the function is rising before this and then dropping after this. So therefore, naturally at 2, it will have a peak point. And with a little bit more analysis, we would have realized that the graph of the function is such that it's equal to 0 at x equal to 0. So it passes through this point. Then at 2, it reaches a peak point, and after 2, it drops. And you can see that at x tending to plus or minus infinity, y is minus infinity, because the x square term is coming with a negative sign. So we would have analyzed fully that this point is 4 or 2 comma 4. So this is our not only local and global maxima. So we would have understood from this that, first of all, from this we would have understood that there is a peak at x equal to 2. So y's value is 4. Okay. Because the function has this kind of behavior, because the derivative of the function we saw was positive in this region and negative in this region. So this would have been that kind of analysis. And from this, now we can also understand that for the function 4x minus x square, if we take the natural domain, then the range, so this is the natural domain, then we can see that the range is in fact minus infinity to 4. This is the range. So we can also see that global maxima is equal to 4, which is also the local maxima at x equal to 2. Okay. And global minima tends to minus infinity as x tends to plus or minus infinity. And additionally, we can see that the function does not have any local minima. Okay, so that is like, you can say, the thorough full analysis of the function. But just about finding local maxima, we saw that we had a very precise step, which is the second derivative test, that we differentiate the function, we redifferentiate it, so we have f prime x and we have f double prime x. Then we see that, okay, at which point f prime x is 0, if at that same point f double prime is negative, then we directly know that there's a peak at that point. So we don't have to do this full analysis of number line and, if required, wavy curve and all this. So I'll just leave you with a minute to analyze this and note down any key points if required.
Sir, can you scroll up for a second?
So resume recording and okay. So I think a couple of you just wanted me to scroll up to the part before this. So I'll just give you a minute with the application of this. Then we'll come back to the condition for local minima also. Okay, so now we will look at the point B and see the similar kind of analysis for second derivative as well as derivative at the point B. So derivative we can see is 0 precisely at the point B, but the behavior of the derivative is, you can say, like the opposite of the behavior that we saw in A, right? So to illustrate this point, so now you can see that the nature of the derivative is going from a negative slope at a point before B to a positive slope at a point after B. But precisely at B, the slope is 0. Okay. So if you look at the derivative of the function, now I'm not too interested in what happened in between, okay, between A and B. But at the point B, now the derivative is changing from a negative value to a positive value. Okay. So you can see that its slope is negative, is positive. You know, the slope of the derivative f prime x is positive. So what we can see now is at x equal to b, f prime of b is 0, but the behavior of f prime x is that it is increasing with respect to x. And it's going from f prime x is negative before b to f prime x equal to positive after b. So therefore, f prime x is increasing at x equal to b. So that means the derivative of this should become positive. So second derivative is positive at b, whereas the derivative is 0. And of course, fx has a local minimum at x equal to b. So now we can see from this, we develop the condition for local minima. Therefore, the condition for fx to have a point of local minima at a particular point is that derivative should be 0 and second derivative should be positive. Positive.
So it's exactly opposite, right?
Yes. Now you can see second derivative opposite हो गया. Second derivative A पे negative था और B पे positive हो गया. Whereas derivative is zero at both the points. So at a peak point, derivative is zero, second derivative is negative, and at a dip point, derivative is zero, but second derivative is positive. So this gives us a clear distinction between the point of peak and point of dip. It gives us an easy way to analyze that if we have multiple points where the derivative of a function is zero, then how to analyze that which of those points has local maxima and which of the points has local minima. Okay, so first we will condense all this information into a simple method, or you can say like an algorithm, and then we will apply it to some examples. Okay, so second derivative test. Okay, for local maxima or minima of a function. So we just follow this simple step-by-step method. So given a function, say y equal to fx. Okay, step one, find dy by dx or derivative and d2y by dx square of second derivative. Okay, then step two, we say what is called find the roots of f prime x, or in other words, solve for f prime equal to 0. So the values of x at which this is happening, so the values of x at which f prime x is equal to 0, these values are called the roots of f prime x. Okay, now these values are collectively called critical points, okay, or turning points, because these are the points at which the function either peaks or dips. So collectively we call them the turning points because the behavior of the function changes. At a peak point, it changes from increasing to decreasing. At a dip point, it changes from decreasing to increasing. Okay. So these are collectively called the turning points or the critical points. Okay. So now a critical point will be either a point of local maxima or a point of local minima. Okay. So note, any critical point is either a point of local maxima or local minima. So how do we differentiate which one of the two is happening? That is where the second derivative comes in, and that's why this is called a second derivative test, that we analyze the value of f double prime at the critical points. Okay, so now our third and final step is check the value of second derivative at each of the critical points. Okay, if f double prime x is positive at a critical point, it means that there is a local minima, and if f double prime x is negative, it means there's a local maximum. So this is of course at a critical point, not at any general point. Then at that critical point, we have a local maxima, sorry, minima, and in this case, okay, now let's apply all this to an actual example. So this becomes 100% clear how we do this. Okay. So we'll take a function like this, y is equal to, let's say, 8x square minus x to the power 4 plus 3. And we're taking the natural domain of the function. So that's all real numbers. So we want to find local maximas and minimas for this function. And secondly, we'll also analyze for the range. Domain is already given to us, and the global maxima and minima. Okay, so we will follow that step-by-step method. So I'm doing this question for our reference. I will give you enough questions for practice, don't worry. Okay. So first step, given the function 8x square minus x to the power 4 plus 3, step 1, find derivative, okay, and second derivative. So that is, the derivative is, as you can see, differentiate this. So it is 16x minus 4x cube. Okay. And second derivative, can differentiate this. So it is 16 minus 12x square. Okay. Is correct? Just verify once.
Yes.
Yes, okay. So now second step, find the roots of the derivative. That is what we call the critical points. You want to find the critical points in the domain. So those are the points where f prime x should be 0. So from above, let's see that 16x minus 4x cubed should be 0. So if we take 4x common, we have 4 minus x square should be 0. Okay. So further we can factorize this and write this as 4x into 2 minus x into 2 plus x is equal to 0. So we have x equal to 0, x equal to minus 2, x equal to 2. So we have 3 critical points, you can see. So our second step has revealed that there are these 3 critical points, critical or turning points. So typically there is a possibility that either 2 are minimas and 1 is maxima, or 2 are maximas and 1 is minima. You'll understand that it's not really possible that all 3 are local maximas or all 3 are local minimas. Okay. So either the shape is like this, so we have 2 minimas and 1 maxima, or the shape is something like this, so we have 2 maximas and 1 minimas. Okay. So this is pointing to something like this. The shape of the graph is either like a W-shaped graph or an inverted W-shaped graph. So step 3 is what we call the second derivative test. We'll analyze the second derivative at each of these critical points, 0, minus 2, and plus 2. So in fact, we can even label them like this, that x1, x2, and x3. We have 3 critical points. So these are the roots of this equation. Roots of 16x minus 4x cubed are x1, x2, and x3. So now our next step, test the second derivative's value at each critical point. You can see that at x1 equal to 0, f double prime of 0 is how much? So it is 16 minus 0. So it is a positive value. So that means fx has a local minima at x1 equal to 0. And what will be y1? It will be f of 0. So substitute in f the value of x as 0. So it will be 3. So the value of that local minima is y equal to 3, but where it occurs at the point x equal to 0. Okay. So now if you just think logically, this is a dead giveaway that this is this kind of graph. Because then this point would be minus 2 and this point would be plus 2. Had it been this, then we should have got a local maxima at this point. Okay. But we are getting a local minima, which means that the in-between point is a minima. So that means it has 2 peaks and 1 dip. But anyhow, we will confirm that with our second derivative test. So that is the whole purpose of this method.
Sir,
Hmm.
what if the second derivative is 0?
Very good question. In that case, the function is little bit more complicated, and there is something called nth derivative test. So if second derivative is also 0, there are two possibilities. One is that the function has neither maxima nor minima at that point. Or again, there's a possibility that the function has maxima or minima, but we have to do further analysis. Okay. But what I will say is that at this stage now, we will not worry about that possibility that if second derivative is becoming 0, because we will be dealing with relatively simpler type of functions in our physics analysis. Okay, that kind of situation, that kind of, you can say that's like a extreme case, or that's like an odd case. Okay, where second derivative is neither negative or nor positive. So that type of extreme or special case, we will learn more about that in advanced calculus. Okay.
Sir, so like y is equal to x cube.
Yeah, if you see the graph of y is equal to x cube, now at the point x equal to 0, it has neither maxima nor minima. Na?
Yes, sir, but the slope is still 0 at that point.
But the slope is 0 and the second derivative is 0. So second derivative is neither positive nor negative. So that's why. Okay. But it doesn't always happen that way, that if second derivative is 0, it's neither maxima nor minima. You can have, I can give you some examples later also. There are functions where second derivative is 0 at a point, which is critical, but at the same time, that critical point is a local maxima or minima. Okay. So we have to do something called nth derivative test. That is, we go on differentiating till we get like either a positive or a negative value of the second derivative. Now, if that nth derivative is an odd derivative, like it's the third or fifth or something, then we have one analysis. If it's an even derivative, like the fourth or fifth or some fourth or sixth or something like that, then it becomes a different case. So I don't want to confuse you at this stage with too many complicated things. Maybe at a later stage, even in physics, we can discuss about it. Okay.
Okay, sir.
Okay, now let's analyze the other three. Okay, so this was one of the critical points. Now, similarly, at a second critical point, which I had taken as -2, the value of second derivative will become 16 minus 4x squared. 4x squared or 2x squared? What was it?
12x squared.
12x squared. Sorry, my mistake. It was 16 minus 12x squared. So it's 12 into -2 square. You can see this is definitely becoming a positive quantity. It's becoming 16 minus 48. Okay. So it is positive of 32, right? Okay. So therefore we can see that it is a positive quantity.
16
Sorry,
minus
it's a negative -32. My mistake. It's 16 minus 48 and not 48 minus 16. So it's a negative quantity. So the moment we can see it is negative, so what we are saying that the function has maxima at x2 equal to -2, and the value of y will become f of -2. Okay. Now remember what the function was. The function was 4x, was it? Yeah, sorry, 8x square minus x to the power 4 plus 3. So the function itself was 8x square minus x to the power 4 plus 3. So the value of the function at -2 is going to become what now? It's going to become becoming 32 minus 16 plus 3. So it is becoming 19. So the local maxima is at spot. And like that, if we check the third point, you'll see it's symmetrical. So at x3 equal to +2, if you check f double prime of +2, you'll get the same value because this term is squared. So you'll get it as again -32 or negative. So that will tell us that the function has again a local maxima. And it's just coincidence that I've taken a function such that the value of the maxima will again be the same as it was at -2. It will again become 19. So again, this local maxima is also having coordinates 2, 19. Just check my calculation also once, it should be correct. Okay, so now we actually have the values of that W-shaped graph that we are talking about. Now, the two peak points are at -2 and +2, but the y coordinates are interestingly symmetrical. They are 19. And the dip point, the y coordinate is dipping to 3. And that's occurring at on the y-axis actually, at x equal to 0. So our local minima is, our dip point is occurring precisely at this point, 0, 3. Whereas our peak points are basically at these coordinates. Okay, people. So Now see, not only we have got all this useful information about the local maxima and minima, now additionally we can also see that if you look at the behavior of the function, now if you just think in terms of number line without even doing that whole, wavy curve method analysis and all that, you can see that at 0 we are having a peak point. Okay, that peak point was, sorry, we were having a dip point, my mistake. Yeah, we are having a local minima. So we are having a dip point of 0,3 it was, right? And at -2 and +2, we were having two symmetrical peak points. Okay. So they were -2,19 and 2,19. So these were peaks. Okay. So obviously, in between here, there's no other maxima and minima. So the function has to drop. It has to rise. Okay. But just to check what's happening on this side, you can also see that the function was 8x square, right? Minus x to the power 4 plus 3. So for x tending to minus infinity, what does y tend to? Y tends to minus infinity, because this x to the power 4 term dominates. Minus x to the power 4 dominates. Okay. And again, x tending to infinity, y again tends to minus infinity because of the same reason. So if we analyze here, the graph has to start from some negative value, in fact a minus infinity kind of value. So we get a general idea that this is how the shape is looking. Okay. So in fact, we also understand one thing which is a bit quite more advanced than this, that overall the function, the power 4 function or the polynomial, will have only two roots. It will have only 2 points where it cuts the x-axis. Okay. But let's say that much algebra is not of concern for us right now. What is more of concern for us is the domain range thing. So domain was already given, -2 plus infinity. So putting all this analysis in place now, we can see that the graph of the function has to be such that when x starts from minus infinity, y is also minus infinity. But it peaks till it reaches the local maxima. Then it starts dipping till it reaches the local minima. Then again peaks, then again dips. And by the time x goes to plus infinity, y also goes to plus infinity. So this is the point 0,3, and these 2 points are at 19. So now we have an idea about the range also. We can see that the function never goes beyond 19 on the y-axis, no matter what x is. So these are also points of global maxima. Okay. So we can see that for this function, the range is from minus infinity to 19. That is the range. So the global minima tends to minus infinity. The global maxima is equal to 19. Okay. The local minima equals to 3 at the point x equal to 0. And the local maxima is equal to 19 at both points, x equal to -2 and again at x equal to 2. And this is also the global maximum. So this is the full analysis of the function, as you can see. Okay. Now you can later, when you're revising today's lecture, you can repeat this analysis with the wavy curve method also that we discussed earlier. Okay. And you'll see that you'll come across the same conclusion when you are analyzing the number line. Okay, you'll see that the derivative, you'll be able to see that in this number line, the derivative of the function f prime x, it will have this kind of behavior, that it will be positive in this part Okay, then it will become negative here. It will become positive here. It will become negative here. This you'll get if you use the wavy curve method. For analysis of f prime x greater than 0 or f prime x less than 0. That is, the function is increasing or the function is decreasing. So in this region, you can see it's increasing. This region is decreasing, then again it's increasing, then again it's decreasing. But now you can see that I have considerably reduced the amount of analysis I have to do by incorporating the second derivative test method for our local maxima and minima. Okay. So that is like, you can say the scope of application of derivative as far as analysis of functions is concerned. Okay. Now, of course, in physics, we have sort of limited application of this according to what physical situation we are applying particular function to. But it's good to know the whole analysis, and of course, it will help you in your advanced calculus later also. So definitely, it's an important aspect of basic calculus for us that using the second derivative test, we should be able to analyze the local maxima and local minima for given function. Okay, people, so that brings today's lecture to a conclusion. Thanks for attending and wish you all the best. Okay. Inflection point, beta, is slightly more technical word, Aryan. Okay. So let's discuss about inflection point, let's say at a later stage, okay, when we are winding up calculus. Okay. Right now, you just understand the points where derivative is 0 as they are called critical points, or sometimes they are also called turning points. Okay. So they are a type of inflection point, but its inflection point also includes another thing in the definition. So let's for the moment, let's just keep it simple. Okay. We'll maybe discuss about inflection points at a later stage. So that's it for today's session, people. Thanks for attending. Wish you all the best. I will send you the notes and the recording, and also an assignment which is dedicated for all this, local maxima, minima, domain range, etc.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay,
Hi,
bye.
sir. Thank you, sir.
Bye, people. Have a nice day. Yeah, Sambhavi, we'll be starting integration in the next lecture itself.
Okay.
Because we have now finished local maxima, minima. Na? So maybe like half the next lecture or more will go into analysis of domain range and all these things. Whereas we'll start the basic introduction to integration next time.
Okay. Thank you, sir.
Okay. Okay.
Afterwards, can you show an
Thank you,
example
sir.
of the type of functions that you were saying where like it has a maxima but the derivative at that point, second derivative?
Yeah, we'll discuss better in the next lecture. When we are winding up this analysis, we'll discuss. Okay.
Okay, sir.